Okay, welcome everybody to today's mini course on matrices. So if you've had a class in linear algebra, the rest of this lecture is going to be pretty boring to you and routine. But if you're rusty on your linear algebra, please listen to the whole lecture. And if you haven't had linear algebra, I hope you've at least seen matrices before. And I'm giving you just the basics, just enough to get you quickly up to speed. Linear algebra is not a prerequisite for the ODE class, but it is helpful if you've had it before. But if not, I can teach you all the basics quickly. And so you're not, if you do a little extra practice versus someone who's had linear algebra, you'll be up to speed in no time at all. Okay, so first of all, what is a matrix? A matrix is an array of numbers or objects, but we deal with numbers or functions. So usually we let I go between 1 and m, and j go between 1 and n. Okay, that's an n. Okay. And so the ijth entry is the entry in the ith row and the jth column. Okay. Often we have to deal with the transpose of a matrix. And so the transpose of the matrix means you invert the rows and the columns. So I'll do an example in a second, but a transpose is just AJI. So for example, suppose we take A to be the matrix 1, 2, 3, 4, 5, 6. Okay, so what's the size of this matrix? There are 2 rows and 3 columns, so it's a 2 by 3 matrix. So up here, the way I've written it, since I is denoting the row, this is an m by n matrix. So in my example, I have a 2 by 3 matrix. And what is the transpose of this matrix? So you take the first row and you make it the first column. And you take the second row and you make it the second column. And then you clearly see that the transpose is a 3 by 2 matrix. Okay, so that's all there is to transposes. Another thing you will run into that we need to know is something called the adjoint. So again, this was the transpose of A. So this is going to be the adjoint of A. And that is you take A complex conjugate transpose. So you take A, you take its complex conjugate, and you transpose it. So that means from the original matrix, if the original matrix is Aij, you do AJI complex conjugate. And it turns out it's no different. One of the things you prove in linear algebra is that A conjugate transpose is the same thing as A transpose conjugate. We're not going to do proofs, we're just doing the bare minimum that we need to know. So that's A adjoint. Now in a real matrix, everything is real, so the transpose is the same as the adjoint. But if you have complex entries, it's different. Okay. Another special kind of matrix we will use a lot are 2 special kinds, really, what are known as row vectors and column vectors. Okay, so a row vector is a matrix that has, let's say a 1 by n matrix. It has 1 row and as many columns as you want. So you might have a matrix that looks like A1, A2, AN. So that's a row vector, okay? And a column vector is an n by 1 matrix. So it has n rows and 1 column. So a column vector would look like this, okay? All right. Okay, so some algebraic properties of matrices. And here's where matrices become very different from just real numbers. Okay. One is equality of matrices. The matrix A equals the matrix B if and only if A and B are the same size and the corresponding entries, the ijth entry of A is equal to the ijth entry of B. So that's where A is the matrix, Aij, and B is the matrix Bij. Okay. All right, so that's what you mean by equality of matrices. They have to be exactly the same size, and things in the corresponding spots have to be equal. Okay. The zero matrix. There is a zero matrix. You pick your favorite size. The zero matrix is the matrix consisting of all zero entries. And there's zero matrices of all sizes. You can make it any size you want. Okay. How do you add two matrices? Okay, so you can add two matrices. Let's say A is Aij and B is Bij. Okay, so we can A plus B is equal to Aij plus Bij, and A plus B exists if and only if A and B are the same size. If they're different sizes, you cannot add them. And if they are the same size, then you add things in the corresponding spots. Okay. All right, so you can do scalar multiplication on matrices. If C is a real number, if C is an element of R or C, if it's a real or a complex number, then C times the matrix A is C times Aij. In other words, you multiply every entry inside the matrix by that number. And it doesn't matter if it's a real or complex number. That's how you do it. Okay. Just multiply everything inside by that. Okay. Before I write down the next, one more we can do. You can do subtraction of matrices. A minus B then is A plus minus 1 times B. Okay, because we defined scalar multiplication up here and we defined addition up here. So term by term, this is Aij minus Bij, and it can be done. You can subtract the two matrices if and only if they're exactly the same size. Okay, you can't do beyond that. Okay. Okay, that's subtraction of matrices. Multiplication of matrices. First, we have to define what we mean by multiplication. Okay, so we can only define multiplication in a particular way. So suppose A, you want to define A times B. So if A is M by N and B is N by K, then multiplication is defined. And it's defined to be the sum from, I don't know, let's say J equals 1 to N of A, I, J, B, J, K. Okay. A, I, J, and I use K for the B, L. Okay. And that gives me C, I, L. So this is the matrix C. So this is how you define C is the product of A and B if it consists of the entry CIL. And when you multiply an M by N times an N by K, you will get an M by K. Okay. And so this is for I between 1 and M and L between 1 and K. Okay. So in reality, that means you have to know your right hand from your left hand. You take a row of A, you multiply it by a column of B, and if it's the first row times the second column, gives you the first row, second column. That should be familiar to you. You guys are engineers, or everybody's seen matrices at least a little bit in high school. Okay, so you can't always define matrix multiplication. Okay, if the middle numbers don't match, if you have an M by N times a K by L matrix, oops, B, okay, K by L, then, and this, the matrix multiplication, not defined unless N is equal to K. So if the two middle numbers don't match, you can't multiply, period, okay? All right, so with that as our definition of matrix multiplication, we'll come back and do an example in one more, in 1 minute. Algebraic property 6 is what I mentioned. So with matrix multiplication defined as we did above, then you can multiply matrices. Multiplication of matrices. And so AB defined as above. And it's easy to see that in general, it is not commutative. AB is not equal to BA in general. So you just can't multiply matrices however you want, okay? It's sometimes it works, sometimes it does not, okay? Okay. And finally, the last algebraic property before we do an example is a distributive property. Oops, I shouldn't have crossed that B. And what it says is that if everything is defined, so if the addition is defined and the matrix multiplication is defined, so if all operations defined, then multiplication distributes over addition, respecting the right and left hand. Things are not commutative. So this is AB plus AC. Okay, but that is not equal to BA plus CA in general. Okay. All right, so let's do an example and pick a problem out of the book in this section. I could just make one up at random, but that's okay. So suppose I, yeah, let me just, so suppose I look at A is 1, 3 minus 2, minus 2, 2, 1, 0 minus 1, 3. Let me take B to be 4 minus 1, 6, minus 2, 5, 1, 3, 0, 2. And let me take C to be 3, 1, 2, 0, minus 1, minus 2. Okay. So A is a 3 by 3 matrix. B is a 3 by 3 matrix. And A has 3 rows and 2 columns. Okay. All right. So let's do some various operations on it. Suppose I ask you what is 3a minus 2b. Okay. So first of all, can you do it? Well, A is a 3 by 3 matrix, B is a 3 by 3 matrix. So I can add or subtract them. That makes sense. So 3 times A minus 2 times B. Well, what is 3 times A? 3 times A is 3 minus 6, 0, 9, 6 minus 3, minus 6, 3, 9. And minus 2 times B is minus 8, 4, minus 6, that's positive 2, minus 10, 0, and then I get minus 12, minus 2, minus 4. And now I subtract things. So I just subtract things that are in the same position inside the matrices. So that's 3 minus a negative 8, so that's 11. 6 minus 6 minus 4, that's minus 10. 0 minus a minus 6, that's plus 6. 9 minus 2 is 7. 6 plus 10 is 16. 3 minus 0, minus 3 minus 0 is minus 3. Minus 6 plus 12 is 6. 3 plus 2 is 5. 9 plus 4 is 13. Okay, so that's it. Okay. Suppose I ask you what is C transpose. So C transpose means we interchange the rows in the column. So the first row, 3, 1, becomes the first column. The second row becomes the second column. The third row becomes the third column. That's it. Okay. So suppose I now ask you and notice C was a 3 by 2 matrix, but C transpose is a 2 by 3 matrix. Okay. All right, suppose I ask you what is A times C. So A is a 3 by 3 matrix. C is a 3 by 2 matrix. The middle numbers match. That means I can multiply, and I'm going to end up with a 3 by 2 matrix. And again, hopefully this is just a review for you. If not, you're going to need to find some resources online or tutorials from the book to practice this a little more, because this will seem strange if this is the very first time you have seen this. Okay, so basically when you multiply matrices, you have to know your right hand from your left hand. You take the left side, the left matrix, take the row. In your mind, you think of standing it up next to the columns, you multiply across and add. So in my mind, for the first row, I think I take 1 minus 2, 0, stand it up next to the column, multiply across and add them all up. That's what that formula, if you think about it, that I wrote down before says. So this is 3 times 1 is plus minus 2 times 2, so that, and then 0 times 1, so that's 3 minus 4, and 0, that's minus 1. And now you take that first row times the second column, multiply in the spots and add. So this is 1 times 1, minus 2 times 0, minus 2 times 0. So that's a 1. Now we do it again with the second column. So that's 3, 2, minus 1. So I'm thinking multiply times each column, squish it down and make it one number. So that's 9 and 4 is 13, minus 9 is 4. I'm sorry, this is a 1, not a 9. It's the way I wrote it. So that's 9 and 4 is 13, minus 1 is 12. Okay, and then times the second column, it's 3, and then 0, and then 2. 3 and 2 is 5. Okay, and now you do it again with the third column. It's bad with ink because you can't, it's hard to erase enough. But that boils down to doing minus 2 times 3, that's minus 6, plus 2 is minus 4, plus 3 is minus 1. And now times the second column. That's -2, 0, and +2. That gives me 0. So that is the matrix A times C, and notice it is a 3x2 matrix. Whoops, oh, golly, none of that was showing. I'm sorry. I'll give you a second to look at that, okay? Okay. And now when you look, suppose next I ask you what is C times B. C is a 3x2 matrix. B is a 3x3 matrix. The two middle numbers don't match, so you can't multiply. Okay. All right, so you just can't multiply. And that happens sometimes. Matrix multiplication is not always defined. Okay. All right. Okay, so that's how you do matrix multiplication. And it's just going to take some practice knowing your right hand from your left hand. You always take a row on the left. You take one row at a time on the left, and then you multiply it times one column at a time on the right, and then you add them up. And for example, the second row times the third column gives you the entry that goes in the second row, third column of the matrix. So it kind of tells you where it goes. Okay, two other properties we need out of this matrix multiplication. There's two other kinds of multiplication. There's something called vector multiplication. Okay, so you think of, suppose that X and Y are n by 1 column vectors. Okay, and suppose I look at, and I'm going to define the quantity X transpose Y as the vector, that's a vector or way to multiply these two column vectors. Because if I just said X times Y, that's an n by 1 times an n by 1, that doesn't make sense. But an X transpose now, because X was n by 1, X transpose is 1 by n. Y is an n by 1. The two middle numbers are the same, so I can multiply and I end up with a 1 by 1 matrix. So, so this always gives me a scalar. Okay. And what is it really by definition? It is going to be sum from I equals 1 to n of xi times yi. Okay. And if you think about that, that's because X transpose Y is going to be, if we think of X as the column vector x1 up to xn, then here is X transpose. And if Y is the column vector y1 up to yn, here is Y, okay? And so now when I multiply, I take the row and I think stand it up next to each other. That's the way I do it in my mind. Cross multiply and add it up. So that'll be x1, y1, x2, y2, all the way up to xn, yn. That's the formula. Okay. So that's how you do a vector product, or one way to do a vector multiplication when you have two n by n matrices. But the more common one, the one you really hear and the one that's more useful, is what's called the inner product, because it turns out being the dot product when you've seen, everybody in here must have seen either linear algebra or calculus 3. So again, suppose X is a column vector x1 up to xn, and Y is the column vector y1 up to yn. Then X inner product Y, this book uses round brackets. Some books use square brackets. X inner product Y is defined to be sum from I equals 1 to n of xi, yi complex conjugate. Okay. Which using this notation before is using the notation from before, it is X transpose Y complex conjugate. Okay. So it's that vector multiplication. This is easier to remember. And so if you think of these as vectors complex with possibly complex entries in Rn, which you can think of a vector in Rn as a vector in Rn, you can think of it as a point in Rn with and then when you look at this is the dot product. This is the same as the dot product of the vectors. Okay, x equal x1 up to x, vector x. This is the way you would usually write it in Calc 3, although usually the vector doesn't always have capital letters. That's the dot product of vectors in Cn, because they could be complex numbers. We will just be forced to work with complex numbers. So we have to be able to be ready to deal with that. Okay. And so notice that if you take a vector x, a column vector x, and you take its inner product with itself, that becomes the sum from I equals 1 to n of xi complex conjugate, which you should remember by our discussion of complex numbers is the absolute value of xi squared. And when you add that up, that is sorry, that's my husband's cell phone, which happens to be in this room. Let me start that one. Cell phone up here. Okay, so so that's the usual dot product of a vector in Rn or Cn, depending upon how you like it to think of it. Whether you have if you don't have complex numbers, this is just the absolute value of xi squared. Okay. Okay. So that gives you the length of the vector. This is the length of the vector x in your calculus 3 notation squared. Because how do you get the length of a vector in calculus 3? You square each of the components and then you add them up and then you take the square root. That's exactly this. Square each one, add them up, and then to get the length of the vector, you have to take the square root of that. Okay. We set, so we define the length of a column vector x by the length of x is defined to be x inner product itself square rooted. Okay, so following along the lines that I just mentioned. Okay, and we say is one definition, and two definition is two column vectors are orthogonal if x inner product y, that's a y, equals 0. Okay. Just like you had for the dot product in calculus 3, because when you had just vectors in R3 or R2, you could think of the dot product as the cosine of the angle between the two divided by the length of each one and got it that way. But this is a more general definition. Really, the definition of orthogonality is given in terms of inner products. So two vectors are orthogonal if their inner product is 0. Okay. All right. Another thing we're going to use is the identity matrix. We'll use this a lot. So the identity matrix We'll always use an I. It's always an n by n matrix. So you have one of every square size. And what you do is you put ones along the main diagonal and zeros everywhere else. So the 2 by 2 identity matrix is 1, 0, 0, 1. The 3 by 3 would be 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so on. We talked about inverses of matrices. So I'm very quickly going through the linear algebra that we need. Okay, so we saw that if you had a 2 by 2 matrix, and we just wrote down the formula and checked it, we didn't derive it, A, B, C, D has an inverse if and only if the determinant of the matrix, which is for a 2 by 2, AD minus BC, is not equal to 0. So the determinant not equal to 0 is a necessary condition for an inverse. And in that case, we had A, B, C, D inverse is D, A minus B minus C. Okay. All right. So that's how you do the inverse of that matrix. Okay. Now what if it's bigger than that? For larger matrices, so for a matrix to have a chance at having an inverse, it must be square. So 1 by 1, 2 by 2, 3 by 3, 4 by 4, square matrix, okay? But every square matrix does not have an inverse. And in fact, what you can prove, and you do prove in linear algebra, A, an n by n matrix, A has an inverse if and only if the determinant of A is different from 0. Okay. All right. So that's the only way you can have an inverse, if the determinant is non-zero. Okay. If the determinant is 0, you don't have an inverse. But you know that finding a determinant is not a fun thing. You have to expand by minors. It really gets to take a lot of time. And so and then once you find that, it's a complicated formula, even if you find the determinant to write down the inverse. It's not trivial like it was for this the 2 by 2 matrices. So what's the best way that we have to find an inverse? Okay. So to find an inverse, the general formula, I'll write it down for you. This is the way I would not recommend to do it. So suppose A is n by n and the determinant of A is not equal to 0. Then B equals A inverse. And let's say B is the matrix with entries Bij. How do you find Bij? What you do is you take Cji, and let me just be sure that I'm writing this down carefully. Yeah, it's Cji divided by the determinant of A, and Cji, where Cij is actually -1 to the I plus j. Okay, So it's really a pain to find the inverses this way. So is there a better way? Yes, there is. I'm really not going to explain the reasoning why, because it takes a good 30-40 minutes. If you've taken linear algebra, I am sure you have seen this. You're basically solving 3 systems of equations simultaneously. So basically what you do is the fast way to find A inverse. Okay. You put the matrix A in here. Say this is an n by n matrix. You put a line there. Now you put the n by n identity matrix there. Okay. And you use the row reduction that I taught you during our from chapter 7 that I taught you way back when we were doing higher order ODEs, to try to get the identity over here. So you want to get 1 0 1 0 0 0 0, the identity n by n identity matrix on the left hand side of the matrix, and then what's left on this side will be A inverse. Okay. If you cannot get I on the left, then A has no inverse. That is provided you've done things correctly. What do I mean by not being able to get the identity? You get a row that turns out to be all zeros somewhere. There's no room for a row of all zeros in the identity matrix. So when you see that, when you're trying to clear and get your identity over here and you get a row of all zeros, that means you have no inverse to that matrix, which happens. Not every matrix has an inverse, okay? So let me give you an example. Let's do an example of finding an inverse of a matrix. Hopefully I will pick one that it has one and one that doesn't have one. So here, suppose I look at the matrix. A is 2 0 0 1 2 0 0 1 2, and I tell you to find A inverse. Okay. So when I go to do that, the first thing I have to do is write my matrix over here, put my identity matrix on the right, and now I start using the row reduction. So the row reduction, and I'm trying to get 1 0 0 0 1 0 0 0 1. Okay. So to get the 1 in the correct place, I take 1/2 row 1. Okay, so that'll be 1 1/2 0 1/2 0 0. Okay. To get and then if I just recopied everything down, I would have cleared row 1. But while I'm at it, let me go ahead and do 1/2 row 2 and 1/2 row 3. Because I can kind of see where this is going. And that'll help me a little bit because now row 3 is in perfect shape to do the reduction from there, even though that's kind of jumping ahead. Before I do that, I need to use this 1 to clear out the second column. This already has a 0, so I just need to get a 0 up here. So I will do minus 1/2 row 2 plus row 1. And that'll give me, here's my row 2. I'm leaving that alone. Okay, so minus 1/2 times row 2, it's 0 and 1 is 1, minus 1/2 plus 1/2 is 0, minus 1/4 and 0 is minus 1/4, 0 and 1/2 is 1/2, minus 1/4 and 0 is minus 1/4, 0 and 0 is 0. Okay, and then I copy down my row 3 because it already has a 0 in the right place. And now the last step is to use that 1 to clear out the 2 numbers above it. Okay, so to get rid of a 1/2, I do minus 1/2 row 3 plus row 2. So that'll be 0 and 0 is 0, 0 and 1 is 1, minus a half and plus a half is 0, 0 and 0 is 0, 0 and a half is a half, and then minus a fourth, and 0 is minus a fourth. Okay. And now to get rid of a minus 1/4 using a 1, I'll do 1/4 row 3 plus row 1. Then I'll get 0 and 1 is 1, 0 and 0 is 0, minus a fourth, I'm sorry, plus a fourth and minus a fourth is 0, 0 and a half is a half, 0 and minus 1/4 is minus 1/4, and then I get 1/8 and 0 is 1/8. Okay, so now you can see I have the identity over here. So what's left over here is A inverse. And A inverse then is equal to 1/2 minus 1/4, 1/8, 0, 1/2 minus 1/4, 0, 0, 1/2. Okay. And when I say A inverse, one thing I should have mentioned earlier is that when you have a matrix A inverse, what's true is that if you multiply, I left off a couple of properties I should have mentioned before. If you take a matrix and you multiply it by its inverse on the right or on the left, you get the identity matrix. Okay, so here's some more properties if A inverse exists. So if you multiply on the right or on the left a matrix by its inverse, you get the identity matrix. That's what you mean by the inverse. It's a generalization of the idea of a reciprocal. If you take a number and you multiply it by its reciprocal, you get 1. The generalization of 1 for matrices is the identity matrix. But you can't say that 1 over a matrix. That makes no sense. What you mean by that is A inverse. You mean the inverse of the matrix. Okay, so that's a generalization of the property for real numbers in terms of matrices. Another property I should have mentioned before is when you take a matrix and you multiply it on the right or on the left by the identity matrix, you get the same matrix back, so long as the multiplication is defined. Okay, so in other words, if A is n by n and I is n by n, then this property is true. Okay, so I failed to mention that earlier. I should have done that. All right, let's do one more inverse of a matrix. Okay, I hope this one works out to do what I want it to do. So this is number 13 out of the book. So take A to be 2 minus 1, 4. And take, well, maybe I have one written in my notes. No, I did not. Okay, yeah, I'm not sure. So let's take this one. 2 minus 1, 4, 3, 2 minus 1. 1, 1 minus 1. Okay, so that's A. And now we want to find A inverse, if it exists. So we write A in a big matrix, which is called the augmented matrix, if you want to learn that terminology. Is the augmented matrix of finding the inverse. And now we just work. So I want this to be a 1 up here. So I say 1/2 row 1. So that'll be 1, 3/2, 1/2. Whoa, I made this really tight. 1/2, 0, 0. Okay. And now I want to get rid of a minus 1 using that. So it'll be row 1 plus row 2. That'll give me a 0. 4/2 and 3/2 is 7/2. 1/2 and 1 is 3/2. 1/2 and 0 is a half. 0 and 1 is 1, and 0 and 0 is 0. And now I want to do minus 1/4. Minus 4 row 1 and add it to row 3. So that'll give me a minus 4 and a plus 4 is 0. That'll give me a -6 and a -1 is a -7. Yeah, that's right. Then I will get a -2 and a -1 is -3. And then I'll get a -2 and 0 is -2, 0 and 0 is 0, 0 and 1 is 1. Okay. And now I want to get that 7/2 to be a 1. So I'll say 2/7 row 2. So that'll be 3/7. And then I'll get 1/7, 2/7, 0. Okay, and now I want to get rid of the -7 using this +1. So I'll say 7 row 2 plus row 3. And when I do that, I'll get 0 and 0 is 0. 7 and -7 is 0. This gives me a +3 and a -3 is 0. 7 times 1/7 is 1 and -2 is -1. Then I get 2 and 0 is 2 and 0 and 1 is 1. And now you stop because you look at this and here's a row of all zeros, okay? And once you get a row of all zeros, you're never going to be able to get the identity matrix. So we can't get I on the left. Therefore, A has no inverse. Okay, so A is not invertible, period. And that's just the way it goes. Some matrices don't have inverses, such as life. Okay. All right, so the last thing I want to mention from this section is that we can have matrices made of functions. So you could have A, I, J of T be in the matrix with entries A, I, J of T. So this is a matrix of functions, okay? And so you can differentiate, you can talk about derivatives. I'm sorry, this is an A, matrix, and entries, blah. That was a brave lip. Okay, so now you can talk about calculus for matrix functions. That is to say, we can say, what is the derivative of the matrix function A with respect to T? And what we mean by that is you differentiate every function inside. Okay. You can say, what's the integral from A to B of A of T dt, where capital A is a matrix function. And what you mean by that is the integral from A to B of A I of T dt. You integrate term by term inside each matrix component, okay? You can, if C is a constant matrix, and CA is defined, then the derivative with respect to T of CA of T is C times dA dt. Okay. If you can multiply, if A and B are matrix functions, so that the addition is defined, so that this makes sense. Okay, they're the same size, in other words. Then this is the derivative of the sum is the sum of the derivatives. Okay. And finally, if A and B are functions of T, or matrix functions of T, and the matrix multiplication is defined so that they're the right sizes, so that this makes sense, then you have a product rule. This is A dB dt plus B plus dA dt B. And you got to be careful. Why? Because matrix multiplication doesn't commute. So I started to write B dA dt. That's wrong. I can't do that, because if I did that, I'm saying basically BA, the derivative of that is the same thing as, I can put it in either order. In other words, I'd be saying it's commutative, and it's not. So if A starts on the left, the product rule version of it has to keep A or its derivatives on the left. Nothing else can happen, okay? So you can get matrix products of functions like that. Okay, so basically that's 7.1 doesn't have very much in it. 7.2 is a very fast review of a lot of linear algebra.